tonight, and I am pleased to announce our today's speaker, Boris Doubrov from Minsk. He will tell us about overdetermined systems of PDEs related to representations of semi-simple Lie algebras. Okay, Borя, you're welcome.
Thank you very much. Thanks a lot for inviting me to give a talk here. And I should say as a disclaimer, first of all, that what I'll be speaking today is probably more about differential geometries and differential equations. I tried to reformulate our recent joint work with two Japanese colleagues, Mashida and Morimoto, on the deformations of rational homogeneous varieties. And they seem to be deeply related to some interesting questions in, for finite type linear PDEs, or actually compatibility conditions for finite type linear PDEs that in turn are the source of many interesting integrable equations. So let's start. I'll start with a very basic and very well-known example that actually serves as one of the most elementary but still non-trivial examples of what I will be speaking today. So this is a way to study projective geometry of surfaces. So just two-dimensional surfaces in three-dimensional projective space. One of the approaches is to encode such surfaces via the following system of PDEs. So UXX is a linear combination of lower order derivatives, and same for UYY. Here U is a function of X and Y, and the coefficients are also functions of X and Y. So this is an arbitrary linear system of overdetermined PDEs, and we need to assume that it's so all compatibility conditions are satisfied, which in this case means that if you differentiate twice by y, the first equation, we get the same as what we if you differentiate the second equation by twice by x, or right-hand side of these equations. So if we assume that these compatibility conditions are satisfied, then this system possesses four-dimensional solution space. So it's each solution is parameterized by values of function u, ux, uy, and uxy at a point. All other derivatives can be expressed from uxx via differentiation of uxx and uyy. So if we now assume that we know we were able to solve the system, so we have a four-dimensional basis in solution space, then now define a map that takes coordinates, independent coordinates x, y, to these four functions. But these functions will now be treated as homogeneous coordinates of a surface in PC. So then what we end up is the image of this map will be a non-degenerate surface in PC, and actually its second fundamental form will be for definite signature. 1, 1. And it is, well, the basis is arbitrary, of course. So of course, the choice of this basis is not unique. We can use any linear combinations, and these linear combinations result in projective transformations of this surface. So this is actually how we encode the projective transformations by the choice, arbitrary choice. So projective transformations reflect the freedom in the choice of the basis of solutions. Actually, we can choose. We can do the inverse. We can take any surface in P3 with this well, in second fundamental form of signature 1, 1, and encode it in the form of this system of PDEs. And actually, well, normally what is done in classical literature, so x and y are taken as asymptotic coordinates, then two coefficients are killed here, a1 and b2. There are four remaining coefficients, and that is for we can write explicitly the compatibility, the system, compatibility equations on these coefficients. I'm not giving them here because, well, it's a simple exercise. What is important is that these compatibility conditions can be used to derive many interesting nonlinear integrable PDEs. Again, I'm not giving here, well, there are lots of examples here, and I just reference an old paper of Zhenya Ferapontov, Integrable Systems in Projected Differential Geometry, which exactly explores this relationship and gives a list of various interesting integrable systems that come up exactly from integrability conditions of this fairly simple system of PDEs. So I should emphasize that even if the system itself is not very complicated and it's finite type system, the compatibility conditions on the coefficients become highly non-trivial subject. And now I'm moving a little bit to the geometry, and well, algebraic geometry actually. So if you look at a trivial system, UXX, UYY equal to 0. So it is easy to see that it corresponds, of course, the simplest system of this kind corresponds to the simplest non-degenerate surface in PC. In this case, it would be quadrics of definite signature, and we know that quadrics of a definite signature can be viewed as images of Segre embedding. So I wrote here as explicitly what it is. We know this double ruling of this Segre embedding. It comes exactly from the fact that we have two copies of P1 here. And the other slightly different, but actually the same point of view on this double ruling of quadrics is that we can identify it with rank 1 matrices of size 2 by 2, but matrices of size 2 by 2 is 4-dimensional space, so we need to projectivize it. We'll end up exactly in the 3-dimensional projective space, and rank 1 condition will transform into the equation on the quadric. And what is important for me is that the space of this rank 1 matrix is actually an orbit of the action of SL2 times SL2. So X and Y are two copies of 2 by 2 non-degenerate matrices. They act on both sides of the matrix, of an arbitrary matrix A for 2 by 2. So that was just a very basic example, which I will now try to generalize, and I will go in the reverse order. So I'll start with some representation of a semi-simple Lie algebra, and I will try to, first of all, turn this into a trivial system of PDEs, finite type system, and then we'll see whether we can add some lower order terms that still satisfy compatibility conditions, and whether we get something non-trivial out of this. So that's, in short, the plan. And now I will try to put as many examples as I could. So, but from time to time, I will still use the language of semi-simple Lie algebras and root systems. For those who is not comfortable with this language, you just can probably ignore this part. I guess the number of illustrative examples I have in this talk will be sufficient to understand what's going on. But as a very first step, I take any semi-simple Lie algebra, any its irreducible representation, and I will try to encode this data in the form of a trivial system of linear PDEs of finite time, as we've seen before, for for this case of equations uxx equal to uyy equal to 0. So let's first do some sandbox examples, so some playground. So we start with the simplest possible simple Lie algebra, which is SL2, and it's k plus one dimensional reducible representation, which is normally denoted as V with index k. So I say that the corresponding system of PDEs is just k order trivial ODE. I will present a general procedure soon, but first let's see how it works on examples. What does this mean that this representation of SL2 corresponds to this trivial ODE of order k? So first of all, should have been k plus one, I'm sorry. So k plus one's derivative of u equal to 0, because now we have the solution space of this equation. That's just all polynomials of degree less or equal to k. This is the basis. And now we have a symmetry algebra of this equation. So it's not very difficult to compute the symmetry algebra. And in this case, let's assume that we deal with fiber preserving symmetries. Actually, I will even restrict further because I'm interested really in transformations that preserve the structure of a vector bundle. But this is the symmetry algebra of this equation, and we see that it has SL2 inside the symmetry. It has this Euler transformation also, just scales all solutions by a constant. And then the space of solutions is a part of the symmetry algebra because, of course, we can shoot by a solution and still preserve the equation. So what happens here inside the symmetry algebra we have was the SL2, the Lie algebra SL2, and its action on this irreducible k plus one dimensional irreducible representation. So k plus one dimensional representation shows up as a solution space of this system, and the initial Lie algebra shows up as a symmetry algebra that acts on the variable x u. So actually, if you think about this in more geometric terms, we see that what we have is OK bundle over P1. So P1 is exactly so x would be the affine coordinate on P1. This will be Lie algebra of projective transformations of P1 if you forget about U part, the U part. So SL2G is actually acts on P1, and this action belongs to OK, and it preserves the solutions. And the solutions are identified with a space of sections of this vector bundle. Again, that might be too geometric or too algebraic, I'd say. So the main point is that if we want to turn representation of a semi-simple Lie algebra into the equation, we expect that the Lie algebra itself will act on independent variables. The solution space will be exactly the representation of our Lie algebra, plus, of course, the action of our Lie algebra will be extended naturally to the vector bundle over the space of independent variables.
Yeah. Excuse me. And what is M here?
Yeah, that's okay. K is here and K here. Sorry, from time to time I choose different notation. I think it should be K here and K here. I'm sorry for the misprint. Okay. So another example, it's again misprint here. So it should be two copies of SL2 here. Take two copies of SL2 and take two irreducible representations now, Vk and Vl. So they correspond to this again a bit strange system of PDEs in this case. So it's case order derivative of u with respect to x is equal to 0, and else derivative of y with respect to else derivative of u with respect to y equal to 0. So k are two integers, u is a function of x and y. And again, we have now vector bundle where all our solutions sit. It will be it's easy to solve. So we understand that this will be polynomials on x and y of degree at most k in x and at most y, L in y. And of course, we can generalize this to any number of copies of P1. And we will be getting, we will get such systems of PDEs, which are very easy to solve, of course. Maybe a bit more complicated example, that's SLN+1 acting on on the case symmetric power of standard representation. And in this case, we end up with the following system of PDEs. It's just all u is a function of x1, etc., xn, and all derivatives of u of order k plus 1 are equal to 0. Then again, u will be all polynomials in x1, etc., xn of degree plus equal to k. So, and again, we have certain vector bundle where all our solutions sit. So it's a case symmetric power of canonical line bundle on Pn. So these are the ways how we encode. Maybe one more example here. Yes. So let's do a bit more complicated example. So G will be SL3 now, and V is a joint representation. So what is important here is that we would need now to look at, to write this in detail, we need to come up with a coordinate system on Heisenberg-Lie algebra on R3, or 3 vector fields x, y, z, where vector fields x and y do not commute. The bracket of x and y is d by dz. Locally, you can think about this as XYZ coordinate system on first jet space of maps from R to R. So the corresponding system of PDEs is this one. So vector field X applied twice to U is equal to vector field Y applied twice to U equal to 0, where U is now a function of X, Y, Z. So this system looks very simple, but actually, as x and y do not commute, it is probably not that easy to see that the solution space for the system is actually 8-dimensional. So it is still a finite type, even if we differentiate only along 2 vector fields among C that form a frame on R3. But because the bracket of x and y gives us the third vector field, we can recover the derivative along Z by doing some differentiation of these equations, or by prolongation of this equation. And actually, this is the solution space. So if we solve the system, we get this very explicit 8-dimensional solution space. And if we now, well, probably I'll say about this a bit later. So if you, for example, if you compute the symmetry algebra for this equation, for the system of PDEs, we will recover exactly the action of SLC on a 3-dimensional space, and it will act naturally on this 8-dimensional solution space. Well, a general procedure now, so if you want to generalize this and recover any irreducible representation of any semi-simple Lie algebra, So the general recipe is like that. So first of all, we have to fix a Cartan subalgebra. So let's assume for simplicity, so in case G is SL, is the simplest, well, SLN, then Cartan subalgebra is just diagonal, the space of diagonal matrices in G, then G plus would be like a strictly upper or triangular matrices in G minus is strictly lower triangular matrices. So we have a decomposition. G is decomposed into G minus, Cartan subalgebra, and G plus. Then we realize G minus as a Lie algebra of left invariant vector fields on the corresponding Lie group G minus. So G minus, small G minus, is a nilpotent Lie algebra. So it is it can be done so that all vector fields inside G minus are actually polynomials. And we denote by xi the elements inside negative part of G, if you wish, that correspond to the minus basis elements in the root system of G. So this is we know that x alpha I would belong to G plus, x minus alpha I will be like opposite elements lying in G minus. For example, in case of cell n, elements xi will be exactly the elements that sit right under the diagonal. And then again, from the representation theory of semi-simple algebras, we know that any such representation is encoded via so-called highest weight vector. It has some coefficients, K1, etc., KL. So we extract these coefficients, and then this is the system. So it's very explicit. So we any representation of a simple Lie algebra is encoded as a linear combination of fundamental weights with non-negative integral coefficients. So these are some numbers that normally are displayed as some marks over Dinkin diagram. And we just take any such number and turn it into the power of the corresponding left invariant vector field on a negative part of the Lie group. And as I mentioned, so G minus is an important Lie group, so everything is actually polynomial at this step. And the fact that what we'll get, so the fact that the solutions of the system will be exactly the representation with the given fundamental weight is not that trivial. It is based on some share theorem in the theory of semi-simple algebras on how to characterize irreducible representations, but it's not very deep and complicated. So we can take it as a recipe. So, and just to give you an example, what kind of equations we can get. So for example, let's go to a more exotic case and take SP4. Then SP4 is 10-dimensional, so it will be split into 4-dimensional G minus, 2-dimensional H, and 4-dimensional G plus. So the vector fields, there will be two vector fields, x1 and x2 in this case, and I've introduced the coordinate system such that these two vector fields will look like the ones that span quantum distribution on G2RR. So if you think about, well, if you use the standard coordinate system G2RR, you'll span and try to get a typical basis that spans quantum distribution here, you'll probably arrive at exactly these two vector fields. And then the systems you will consider will be like this ones. And again, well, to solve such systems explicitly, even for some small K1 and K2, is it's already an exercise. If you try to do it by hand, a computer will probably do it much faster, but the dimension of the solution space will go very, very fast, depending on K1 and K2, because that's the formula of the dimension of the reusable representation. So again, similarly, very simple, in very simple way, we encode explicitly representations of SP4. And of course, we can play around and come up with similar calculations and examples for other semi-simple algebras. Well, this construct is actually very well known in the theory of rational homogeneous varieties. I'm not giving you explicitly the definition of a rational homogeneous variety. Instead, I will use the above construction to at least explain what it is. And as we've done before, so of course it's probably not. Well, we have as I mentioned. So we have the solution space of dimension, which is exactly the dimension of our representation. So it's a finite type system. So let this dimension be k plus 1. We have a basis of k plus 1. So we can choose k plus 1 elements that form a basis of the solution space. And now play the same trick as we've seen for surfaces in P3. So we turn these functions, which are solutions, into projective coordinates of some variety in Pk. And as the basis is arbitrary, this projective variety is defined up to projective transformations. So what we'll get is exactly what is known as a rational homogeneous variety. And it coincides with the orbit, with an orbit of the Lie group G acting on the highest weight vector of the representation V, or to be precise, on the projectivized V. And it is known to be the only closed orbit when G acts on projectivization of V. So it's similar to this example of rank 1 matrices of 2x2 matrices, as we've seen for surfaces in P3. So, and these rational homogeneous varieties are well studied a lot in both algebraic geometry as well as differential geometry that is related to algebraic varieties. As a manifold, this variety is known to be isomorphic to a certain parabolic homogeneous space. So it's G mod P, where P is a parabolic subgroup in G. Again, if you don't know what it is, it's not that important here. Just a few examples here. We've seen that if you take a trivial equation, trivial ODE, then we get the solution space, and if we turn the solution, the basis of the solution space into projective coordinates of a curve, we'll get exactly what is known as rational normal curve in Pk. It's an embedding of P1 into Pk. Well, in an affine chart here, because x is an affine coordinate here, but it can be also made global. Segre variety. So this is the case where we take we assume that our function u depends on r variables x1, etc., xr, s variables y1, etc., y s, and we take all cross products as projective coordinates. Then what we recover exactly the classical Segre embedding of PR times PS into PRS plus R plus S, and this is the corresponding system of PDEs. So again, classical embeddings are normally exactly this rational homogeneous varieties, and they also correspond to some systems of PDEs. Similarly, Veronese variety corresponds to this system, because we should have only quadratic functions here. So to encode the space of all quadratic functions in R+1 variables, so we should write this as a system of third order. And so Veronese embedding is also encoded via this kind of construction. And finally, as we've seen, so if you take actually, if I move back and look at this 8, yeah, so I have these 8 functions. They define a certain embedding of 3-dimensional space with coordinates x, y, and z into P7, because, well, we have 8 homogeneous coordinates. So it turns out that this thing is exactly what is known as a joint variety of SLC. So it consists of all rank 1 nilpotent 3×3 matrices. And it can be identified with a homogeneous space of SL3 quotiented by upper triangular matrices, which is a flag variety of R3. So the space of all lines and 2-dimensional subspaces that contain these lines. So that was the first part of the talk, and the main idea is again that any any representation of a semi-simple D algebra can be encoded as a solution space over a certain finite time system of PDEs, which can be constructed very explicitly. So what is next? So suppose we have now this linear system of PDEs that corresponds to the representation of a semi-simple D algebra. So we want these operators delta alpha that forms the system to be to have only the terms of highest order. So in the trivial system, and it's not actually the case. For example, if you can go to this example here, for example, so this is a part of our system. So if you start expanding this equation, of course, this z and t, which are coefficients at dy, dz, will show up and will form terms of lower order than k2 plus 1. So to make sure that we really have equation that has only terms of highest order, we would need to use the language of filtered manifolds. So very shortly, what happens here is that our space of independent variables will have an additional structure. It will have a bracket-generating vector distribution. So, for example, here in case of this SL3 example, we had 2 vector fields and they span a contact distribution. And this is what happens always with this parabolic homogeneous spaces and rational homogeneous varieties. So we always get an additional bracket-generating vector distribution. So, and it defines a filtration on the tangent bundle of M. So D itself, so this vector distribution is usually denoted by D. So D is first element in this filtration. By tradition, it's this filtration is marked by negative numbers. So it's T minus 1 of M. Then T minus 2 is what we get if we take all brackets from D plus D itself. Then T minus 3 will be what if you take one more bracket with D and so on. So it will, bracket generating means that at the end it will completely non-holonomic in other terms, that finally it will span all tangent space of M. And mu is a number of subspaces in this filtration. So the length of this filtration is normally called the depth of a filtered manifold. And for example, a contact manifold, a standard contact manifold is depth 2, and contact or Cartan distributions of jet spaces normally have depths k plus 1, where k is a jet order. So what we want to define, we want to consider weighted degree of linear differential operators, and we do it like that. So if a vector field lies in T minus RFM, we say that it's a linear operator of weighted degree order I. And normally it can be also encoded by assigning some weights to variables. For example, again, if you go back to the example we've seen before, so if you have our manifold is G1 of webs from R to R, it's a filtered manifold of depth 2, where D is a content structure. So if you choose coordinate system x, y, z, where z is y prime, so this is what spans contact distribution, and then x and y will be first order operators, but their bracket, which is dy in this case, will be already of second order operator. So we see that even if we take only one derivative, that's a derivative along the directions that lies outside of the contact distribution. So we count it as we treat it as a second order operator. And it's equivalent to say in this case that variables x and z have degree -1 and y has degree -2. And then these operators will become linear homogeneous operators of degree exactly 1. So z has degree -1, so d by dz has degree 1. And similarly here, d by dy has degree 2, but it's multiplied by z, so in total it will be exactly 1. So if we look at this, then if you define our order of operators using this weighted order idea, or the idea that comes from actually the theory of filtered manifolds, then the systems we get from the construction, from the representations of semi-simple algebras will always have highest degree terms on. So why we need this? Because I want now to deform them, and by deformed system I mean that I add terms of lower weighted degree. So that's essentially what I'm trying to explain here, is that we keep the symbol of the system the same, but we treat we define the simple in the terms of in the weighted terms. And now, so this is what I would call a deformed linear homogeneous system that has the same symbol as coming from the representations of simple Lie algebras. And again, just to simplify the construction, I say that such system is compatible if its solution space still has the same dimension. Probably it's not the most typical definition of a compatibility, but as we are in the finite type systems, we just want to make sure that our solution space stays the same. Dimension of the solution space stays the same. For example, let's now look at this joint variety of, in the case of a joint variety of SL3. So our trivial system was x squared u equal to 0 and y squared u equal to 0. Now we add arbitrary first and zero order terms. And first order terms will include only derivatives along vector fields x and y, no derivative along the third vector field, and these are zero order terms. Where all this u and a, b, c are functions of x, y, and z. It is actually quite highly non-trivial to check explicitly what does this mean that the system is compatible, you actually, since now it is x squared y squared is not the same as y squared, x and y do not commute, one needs to prolong the system 4 times before this system closes up and all compatibility conditions are shown here. So the compatibility conditions will be equations up to order 4, nonlinear equations on coefficients A, B, and C here. Now we want to say what deformations are trivial and what are non-trivial. So the trivial ones are those that come from a trivial system. So the one which has 0 on the right-hand side by using a change of coordinates, if you wish. But we only allow these changes of coordinates. So here x is our independent variables, mu is a single dependent variable. So we allow any transformations in independent variables, and only these transformations in independent on dependent variable, because we want to preserve the structure of a vector bundle. So these are exactly the transformations that preserve the structure of vector bundle. So of course, if you apply such transformation to a trivial system, we'll get some tail or some non-trivial right-hand side, but you consider this as trivial deformations. And now the main question is, suppose we start with a system coming from a representation of a semi-simple algebra, which of them do really admit non-trivial deformations? So it might sound a bit strange, but as we'll see very soon, there will be only very few of them. And for most of such systems, compatibility conditions are simply too strong. So if you assume compatibility conditions, then this will imply that such system is trivial. So it's just a change of coordinates for a trivializable system is trivializable. So it's just a change of coordinates for the trivial one. Just as an example of a non-trivial deformation, I give you of the system related to SLC. I show you this one. So epsilon is any constant parameter here, and again, it can be shown that such a system is compatible, that it still has 8-dimensional solution space, but it has smaller symmetry, so it is non-trivial. So it is, of course, such change of coordinates does not change our symmetry algebras. So if you end up with something that has smaller symmetry algebra, we know that this is a non-trivial deformation. And actually, this can be solved explicitly, and yeah, well, that will be on the same slide. So where this terminology comes from, a very quick overview of what are the deformations of racial homogeneous varieties. So if you have any deformation, then we again have the same dimensional solution space. We still get some well-defined submanifold in PK. And this submanifold will be exactly a deformation of the racial homogeneous variety. And these deformations are studied a lot in algebraic geometry. So this is not just an arbitrary deformation of a submanifold, of course, because it would have been a trivial thing. So what this kind of deformations preserves, so because we really deal with deformations that have the same symbol, so we keep the same symbol of a system of linear PDEs and only deform the right-hand side or change the right-hand side. So this fact that we have the same symbol will be reflected in the geometry of this submanifolds by the fact that they all have the same fundamental forms. So in projective differential geometry, we may define not just in any dimension, we can define not just a second, but also third, fourth, and higher fundamental forms. So what we'll get will be a deformed racial homogeneous variety, but it will still have the same fundamental forms as the original one. And for example, for the system I've shown you on the previous slide, these are explicit deformation terms if you wish. So the black part corresponds to the original rational homogeneous variety, and the red one shows how it is deformed. What are the extra terms here, and this is a non-trivial deformation. And now in this theory, deformation theory of rational homogeneous varieties, that was and still in some parts is a big question. Which of these rational homogeneous varieties can be deformed and which cannot? And so I think the pioneering questions or pioneering works in this direction were done by Griffiths-Harris in the late 80s, and then Landsberg-Robler, Wang Yamaguchi. These are all, and what is really very special about this theory is that this is a case where local differential geometry techniques is used to solve problems in global algebraic geometry. So in the way that this question of rigidity or characterization of certain varieties by their fundamental forms, well, is still investigated a lot in some other setups. And that's also one of the goals of this talk, to show that if you translate, this question can be translated quite naturally to the language of PDEs, and this might lead to some interesting bridge between these theories and maybe some new applications. So the main result, which was partly done initially by Landsberg and Robler, I think in 2008, and me, Mashid, and Morimoto finished this in 2021. So we proved that invariants of such deformations of rational homogeneous varieties are encoded by a certain cohomology space of Lie algebras. So I think all terms here, except maybe this sign plus, are already defined. So G minus is a negative part of the Lie algebra. SLV is where we embed our G during when we define the representation. So this is just first cohomology space. Plus means because G carries some natural grading coming from the root system. So plus means that we look for all elements in this cohomology which have non-negative, strictly positive degree. And again, such cohomology spaces are not new. They were quite actively, they did appear in some other works. And there is a well-known constant theorem that provides kind of a recipe how to compute such cohomology spaces for actually arbitrary key, not just first cohomology, for in a very general setup. And this is the real recipe, so that it was turned into computer program that is available online. So today, if somebody wants to compute such cohomology, it's not really important. Well, it's really a mechanical exercise, just to enter all the data on the website, and as a result, one gets representatives in this cohomology space. In particular, if this cohomology space vanishes, then there are no invariants of the deformations, and therefore any such deformation will be trivial. So vanishing of this cohomology gives us a very efficient criteria of whether a given rational homogeneous variety can be deformed or not, or in other ways, when compatibility conditions on the deformed system of PDEs imply that this is a trivial deformation. And one case where it was all explicitly computed, where G is, or complexification of G is simple, then it's again a simple exercise in the algebra theory to compute this cohomology, and it turns out that we can enumerate all possible non-trivial, all cases where there exist non-trivial deformations. And as you can see, there are very few of them. Well, these are minimal embeddings. There are also re-embeddings, but they're normally not really very interesting. So what is here is just three cases where we take Veronese embeddings of PEL, projective space, then quadratic hypersurfaces in of the L-dimensional quadratic hypersurface, so it sits in PL plus 1, and then the joint variety of arbitrary SL, not just SL3. And for each of these three cases, we can actually write down explicitly the systems of PDEs. So for Veronese embeddings, I think I've done this already.
Boris, I'm sorry, 1 minute. What is re-embedding?
Re-embedding is, yes. So re-embedding is when you embed, for example, a quadratic surface in PL plus 1, and then you use Veronese embedding to embed PL plus 1 into higher projective space.
Okay.
So as a result, you get QL embedded, quadratic hypersurface embedded in a very high dimensional projective spaces. But actually, it comes as a re-embedding of and similar for other things. So you can use one Veronese embedding to embed PL into P, well, whatever dimension, and then use another Veronese embedding, so we can re-embed it again further. So for this, and these are the systems. So for Veronese embeddings, I think I wrote this explicitly already. For quadratic hypersurfaces, we had it in case of P3, so Q2, and this is how the system looks like for general L. Again, not very complicated. So probably this is the system that defines the that corresponds to quadratic surface of positive signature, and similarly we have for a definite signature. And I should say that again, such systems and a general projective geometry of surfaces, hypersurfaces in PK was studied a lot by the School of Japanese mathematicians, Sasaki, for example. He was using a lot the terminology of PDEs to study projective differential geometry of hypersurfaces. And it's really amazing that these works of Sasaki are almost one-to-one to works of Goldberg and Akis, but they use different languages. Language of PDEs and language of differential forms. And finally, for the joint variety of SL plus 1, so this is a flat system. So again, we have system of second order, but we have pairs of non-commuting vector fields, and the bracket of xi and yy is the same dz, d by dz.
So
that's
sorry.
Yeah.
So these are the only systems that admit non-trivial deformations. Yes.
Yeah, this is only systems where adding some non-trivial right-hand side of lower order, and assuming compatibility conditions would lead to something non-trivial. So, but again, this is only a subclass of course of linear finite type systems that correspond to representations of semi-simple Lie algebras. One can try to take any linear finite type system of PDEs and still try to deform it. And actually, I'm coming now to the end of my talk. There are some discussion with open questions. So first of all, this talk is based on as I mentioned, on our paper with Mashida and Morimoto, which was published in Sigma in 2021. So in this paper, we also treat systems of PDEs with arbitrary symbol, linear systems. So we always stay within the case of linear finite type systems of partial differential equations. But the symbol is not necessarily one related to representations of simple algebras. But still, we use the language of filtered manifolds, so we always deal with not a classical symbol of PDEs, but weighted symbol. So we assume that the space of independent variables is equipped with filtration or with some completely non-holonomic distributions that defines as first-order vector fields. And the brackets will define as second-order vector fields and so on. The problem is, and this is why I'm really speaking here about the semi-simple representation, the problem is that computing the corresponding cohomology space, and we do have similar cohomology space, without any additional assumptions is not feasible. It becomes a very challenging problem. Still, I would say, I think that, so we do get some systems where there are deformations and non-trivial deformations, and some systems that do not have deformations. And of course, we've seen many, or at least I've seen many talks on integrable PDEs, which start with the fact that let's look at a certain system and impose compatibility conditions. And this system is normally this, not necessarily finite type system, but some very simple system of PDEs, and they all come from this class of PDEs which admit non-trivial deformations, because compatibility conditions lead to some non-trivial integrable PDEs. So systematic analysis of potential integrable equations that come from even those three classes of systems is, I think, completely open. So maybe some work was done on, well, quadratic surfaces in PC. Maybe Sasaki did some work, but I don't think he ever treated higher dimensional case and the classes of hypersurfaces that correspond to some other interesting integrable PDEs. And most interestingly, I'm really very much interested in the third case, in even the simplest one, where we start with an adjoint orbit of SL3. This seems to be really a non-holonomic analog of projective geometry of surfaces. So there are a lot of similar geometry constructions. So I would expect that, in particular, some interesting integrable PDEs show up out of compatibility conditions for these systems. And that is maybe a question to this group. I'm not really aware of any integrable PDEs where it is important that variables, independent variables, have different weights. Because when we study such case, it's really essential that we treat derivative with respect to z as an operator of degree 2, not 1. And this, of course, changes the notion of integrability of such systems. Well, so I think that's it. I'm at that in my talk. Well, is there any questions or discussion?
Yes, Boris, thanks a lot. Well, questions, remarks? So are you going to deal with integrable equations that arise from these constructions?
For SL3 case, for sure. Because the problem is, of course, that the systems, and I've seen that, probably can show you again the setup here. So the system is very similar to what we get in projective geometry, and we had I think Veselov-Novikov integrable systems, that stationary systems that are almost immediately appear in case of projective geometry of surfaces. Here, things are very much more complicated because the solution space is not 3-dimensional but 8-dimensional, and as I say, to write down explicitly integrability systems, compatibility conditions, one needs to differentiate this 4 times. So compatibility conditions in projective geometry, compatibility conditions show up as second-order equations on coefficients, on these coefficients, where here it would be 4th-order equations. Moreover, they will use differentiation not along the holonomic variables, but they will use non-holonomic vector fields that do not commute. And I wonder if something like this was already known.
Well, Boris, if you have results in future, let me know. And
Yes, absolutely.
Yes. Okay, thank you. Thank you very much. So thank you to all who joined us tonight.
I have a few questions.
Wait, of course, please.
You consider real algebra over a real field?
This here in the talk, yes, but most of these constructions will work over complex numbers as well.
Okay, and then coefficients A, B, C are real or complex numbers, yeah?
In real case, reals. In complex, they would be complex,
complex numbers.
Holomorphic, yes. Well,
Yes.
at least
And
analytic.
Yes, I understand. And correspondingly, X and Y is a real or complex field or some manifold.
Yeah.
I see. Thank you. Maybe I will write you. I have some questions about some details, but thank you very much.
Yeah, not all. Thank you. And I can also send the presentation.
Yes, please send it to me. We'll put it on our site. Yes, it will be nice. Yes, thank you very much. More questions? More remarks? Okay, thanks a lot, and I hope that we will in some time hear continuation of this talk. So unfortunately, the next Wednesday is skipped, and we meet in 2 weeks on 21st of May. Thanks a lot and goodbye, Boris. Thanks a lot again. And
thank you.
Bye-bye.
Bye-bye.
Bye-bye. See you in 2 weeks.